Hi folks, 3 more lessons to go. We've got 6.1 solving trigonometric equations. This has a lot to do with 5.3 when you're thinking about inverse trig functions, and I'll show you why algebraically in a second. But first I think it's good to think about this graphically. If we graph 2 cosine theta plus 1, you just learned that the 1 bumps up your graph, your cosine graph, up 1 unit, and the 2 has to do with the amplitude. So this is what our graph looks like, centered about the midline 1, and it's bumped up with an amplitude of 2 units. So it goes above and it goes below, down 2 units. So that's just a little review. So that's what this function, we'll just call it f of x, is equal to 2 cosine theta plus 1. And this is off of so we're going to call this f of x. And like I said, this is off of Desmos, so you could use this to help you, assist you to verify your answers. I'm going to say let g of x equal 0, and that's just the x-axis, so this is g of x, which is equal to 0. So the question is, when is f of x equal to g of x? Okay, so we want to figure out which values. And remember, what you're doing when you're solving functions like this or equations like this, you think about what it means graphically. It's where the two graphs intersect. So this horizontal line, when is it intersecting this graph? And we are skipping that section 6.2 numerical methods, but I think that you can just use numerical methods, and that's with the graphing calculator to help you, assist you, and check your answers as you go. And it's nice to have that visual because look at this cosine graph. It goes on and on and on forever and ever and ever. So it's not just at this point that x in this case is equal to 2 pi over 3, right? It's also x could equal 4 pi over 3 and 8 pi over 3 and so on from there. So this pattern, the reason, and then this is the other angle, so 4 pi over 3. If I said 4 pi over 3, I'm doing this for a reason to break it up. It also can equal 10 pi over 3. Whoops. Put a comma there, 10 pi over 3, and so on. So this is where they intersect, right? And basically, we're going to write this and we're going to go up to the unit circle. So let's do that. If I solve this equation, I want to isolate the trig term. That's a technique that we will do sometimes, okay? I'll show you other times when it's not appropriate. So I'm going to subtract that 1, and I'm going to put the 1 over on the other side and divide by 2. So cosine theta is equal to negative 1/2. So that's just subtracting the 1. So minus 1, and then I get 2 cosine theta equals negative 1, divide by 2. So then I get this, cosine theta equals negative 1/2. Well, basically, remember, this is a trig thing, inverse trig. So what angle gives an output for cosine of negative 1/2? Where is that on the unit circle? That is the question. You can see it on the graph, but remember all the graphs come from the unit circle. So let's go back up and think about it. Well, cosine is the x value. Here's a negative 1/2. Here's a negative 1/2. If we think about radians, that's 2 pi over 3, okay, or 120 degrees. Hey, look, there's your 2 pi over 3, okay? But it could also go all the way around the block, all the way around the circle, and it could be 8 pi over 3, right? And I could also go back from there, and it could be 2 pi over 3 minus, right, another 2 pi, so it could be negative 4 pi over 3, okay? So it could be this one, and so on. So do you see how it continues on? So the hardest part of this lesson is how to write that as a solution. And what you do is you're going to say, well, oops, it's not x. We're dealing with theta. Theta is equal to, I'm going to say 2 pi over 3 plus, I want to add on a 2 pi. Whoops. I'm jumping the gun there. And I am going to put a k because k could represent any integer. So that you can put 0, plus or minus 1, plus or minus 2, and we don't have to write this each time, but it makes sense. If k is equal to 0, then you have 2 pi over 3. If k is equal to 1, you are adding 2 pi over 3, and that brings you to the 8 pi over 3. If k is equal to negative 1, that brings you back to the negative 4 pi over 3. And you can check this by doing the radians. Sometimes if you're confused in radians, which I do want your answers in radians, you can go to degrees. So if you have 120 degrees, that would start us right here. If we were doing this in degrees, 120 degrees plus 360, well, let's just do it this way, 360. So that's 0, 8, 480 degrees, right? Put dollar sign. So there's a 480 degrees here. So if you think about this in radians, we would be saying that theta could equal 120 degrees plus 360k. Okay, so that would represent the solution in degrees. Now, this is only one of the angles. So let's do the other angle in a different color. How about some red? And remember, we have this solution down here. So theta can also equal, we need it slightly darker, don't we? Theta can also equal 4 pi over 3. So if it's 4 pi over 3, do you agree that if I go around one full rotation, 4 pi over 3 would land me at 10 pi over 3? Okay, so that would be plus 2 pi. And if I went around again, that would land me on the next if we looked at the graph. If I was at 4 pi over 3 and I subtracted 2 pi, that would land me at negative 2 pi over 3. Okay, so that's where the k comes in. So when I talk about it, rather than writing the plus or minus 1, 2, and 0, you can also say that k is an element of the integers. That's how I like it, because that's a math lingo thing. K is an element of the integers. And the integers are all the whole numbers and all their negative counterparts and 0. Okay, so that represents anything. So if you're confused on this concept, and we're going to keep doing it, play around with those numbers by just saying, okay, well, what is 2 pi over 3 plus, let's do, because we said 2 pi k, 2 pi times 2. Okay, so that would be 2 pi over 3 plus 4 pi. Got to get a common denominator, multiply that by 3 and 3. That's 12 on the top. So that's equal to 14 pi over 3. Okay, so that's another solution. But that's just going around the block, like I said, because this is cyclical and it keeps going and going. Remember how inverses, we restricted it, but now we're kind of opening it up to all solutions. So I just wanted to point out this example because it's in the book, and all of the book's examples in this section are really good. So I highly recommend you reading them. They're pretty straightforward. When you're solving this, you can think of, once again, this is a function, and graph that, and graph the line y equals 1/2 and see where the two intersect. That's what it would mean graphically. Algebraically, I'm asking myself, when is this cosine value equal to 1/2? Okay, well, once again, the unit circle is so handy here. You can see that cosine of 1/2 is at pi over 3 and 5 pi over 3. So when you have something other than theta inside, right here, it can get a little tricky because you're like, you get confused on what theta is specifically. Because it's not just theta now, it's when 3 theta is equal to pi over 3. And then just to make things easier, what they did, rather than saying 5 pi over 3, we're going to just say plus or minus pi over 3. So that covers all of our bases. So if we're here at pi over 3, you can see that if I add 2 pi to this, I'll get back around there, and another 2 pi, and so on. And same with the negative pi over 3. If I add 2 pi to that, and 2 pi to that, or subtract 2 pi, it brings you back to where you started. So this 3 theta is equal to plus or minus pi over 3, and then we can say plus 2 pi k. Well, you've got this 3 theta here, and we don't want 3 theta, we want theta. And so what we're going to do is we're going to solve for that. We'll multiply everything by 1/3. So squeeze in a little 1/3 to each term. And you will get that theta, because the 3's cancel out, is equal to plus or minus pi over 9 plus 2 pi over 3k. Okay, so that represents every single solution. Now, if you get confused with this, just write out a few. Keep adding 2 pi and see if you notice a pattern with the k. Remember, k is an integer, so it's an element of the integers, so it can represent any positive or negative integer, number, whole number, or 0. So sometimes you have to use the Pythagorean identity or other trig identities to clean up your solution. And since I have a cosine squared and a sine squared, I'm going to substitute one for the other so that I have everything in terms of sine or cosine. In this case, I think it's easier to let cosine squared equal 1 minus sine squared theta from the Pythagorean identity. So I'll substitute that in. So I have 1 minus sine squared theta minus sine squared theta equals 1. And the book has a couple of examples of this. Distribute the 2, so it's 2 minus 2 sine squared theta minus sine squared theta equals 1. And now if I combine like terms here, I've got this minus 3, so, and then 2, so it's 2 minus 3 sine squared theta equals 1. I'm going to subtract the 1 from both sides, or the 2, excuse me. So now I have negative 3 sine squared theta equals negative 1, and divide by negative 3. So that gives me sine squared theta equals 1/3. Do you remember how you'd solve a quadratic equation like x squared equals 1/3? Take the square root of both sides. To eliminate the square, x equals plus or minus 1 over the square root of 3, because we know the square root of 1. Same goes with this. You can square root, so you've got sine theta is equal to plus or minus 1 over the square root of 3. So now, this is not a common thing on the unit circle, as you can see. But if we think about this and where it is, we've got positive 1, and when is sine positive? Sine is positive when the y's are positive, which is up in quadrants 1 and quadrants 2. So I don't know exactly where this angle is, but it's going to be, I'm going to say that theta could be here, and theta could also be over here, whatever that is. Okay, so it could be this whole length or just this length. And then also, since we have a negative, it's also going to be that symmetrical point right there. So it can be here and here. So if I think about what my values are, well, from here, from this angle, you can see that on this line keeps going, extends. So if I added pi radians to that, that would get me here. And then if I added another pi radians, it's getting a little sloppy, that would get me back to where I started. So this one we have to use the calculator for, and that's okay. And we're going to do, remember it was sine, we're looking for, I'm trying to show that, we'll go back to that. So we want to make sure that we're in radian mode because your answer should be in radians. If you wanted degrees, you can always go to degrees as well. But we want radians, so we're going to go second sine inverse of positive 1 divided by the square root of 3, close parentheses, and again, so that's 6.615, we're going to say. So theta can equal 0.615. Now that was for the positive, so let's do the negative. And you know what I'm going to do? Second entry gives me my thing again. I'm going to use that same thing and insert a space and put a negative. Probably by that time I could have the same. So it's just the opposite. So it's negative 0.615. So theta can also equal negative 0.615. So if you think about where these radians are, well, this is probably going to be our negative 0.615, and this is our positive 0.615. So to get all of these and to cover this angle over here, I can say that theta can equal 0.615, and if I do plus or minus, let's just do positive. And if I add basically pi times k, that would cover all my bases there. If I did theta equals negative 0.615 and I added a pi times k, that would be this angle and then this one up here. So I know it's kind of crazy to think about, but that's how you do it. So remember we got down to sine theta, so I graphed just sine theta, and then I graphed the line y equals 1 over the square root of 3 and y equals negative 1 over the square root of 3. And if you do that, you can see that here this represents that 0.615 that we found. So 0.615, and then down here that represents that negative 0.615. And if we add pi to all of those, this would give me this one, and then it's like every other, so here and here. And then if I start with this one and add pi to that, that brings me there, here, and here. So it represents. The other reason why I wanted to show you this is great because this is Desmos. So this is a numerical way, meaning we're not doing it algebraically and exact. We're using some kind of graphing utility to approximate our answers, and sometimes that's the only way you can do it. So this is always a great way to check and see what your solutions will be. So here's another fun one that we have to substitute 1 minus cosine squared theta in. So I'm going to do that to quantity 1 minus, I think I said cosine, but I meant sine squared theta, plus 3 sine theta equals 0. So if I distribute this, I have 2 minus 2 sine squared theta plus 3 sine theta equals 0. And if I clean that up, and I'm going to put, basically, just to make my leading term, which will make sense in a second, positive, I'm going to bring everything over to this side. And you'll see kind of why. Because now that gives me positive 2 sine squared theta minus 3 sine theta. You can just change the sign on everything. Minus 2 equals 0. Now this, as I used to say in my calculus class, smells like a quadratic. So this is where your strong algebra skills come in handy. So what we're going to do is we're going to say I'm going to do that right here. Let sine theta equal x. So remember, this is equivalent to sine theta quantity squared. That's what that squared means. So now I have 2x squared minus 3x minus 2 equals 0. And look, it's a simple old quadratic. So remember how you solve quadratics? How can you solve them? Can you factor this? Maybe. Maybe it's factorable. Or what's the other way to do it? Quadratic formula? So you can always use the quadratic formula. I think I might show you guys both ways. So this is factorable. I think number 7, which is one of yours, is not factorable. So you're going to have to use the quadratic formula and your calculator to get the exact value. Kind of like what I just showed you on the last example. You do the cosine or the sine inverse of the value on your calculator, and it'll give you a decimal approximation. So um, if I factor this one, I think the 2x times 2, and then if I put the 1 here because 2x times 2, I want a negative here because negative 3x, and then I put a plus here. That's positive x, and negative 4x gives me negative 3x. So that implies, remember, you get to set each of those equal to 0, and x minus 2 equals 0. So that tells me from this one that x is equal to negative 1/2, or x can equal 2. Now, remember what x was equal to if we substitute what we had originally said. We said that we let x equal sine theta. So I'm going to say put that sine theta back there, and now you have a simpler problem. Sine theta equals negative 1 over 2, or sine theta equals 2? What? Is that possible? It's not possible. Think about the graph of sine. It goes as high as 1 and as low as negative 1. This is out of our range, and remember, we're thinking about the unit circle. It's not possible for this to equal 2, okay? So this is out. This is no solution there, but we still have a solution, so you don't even need to write that. You just don't need to consider that. So the only thing that we're considering is this negative 1/2. Okay, so sine theta equals negative 1/2. When is that? What values of theta give you a negative 1/2? Remember, that's the y values. Well, theta could equal, if you're thinking about the unit circle, could equal negative pi over 6. So we have, let's just look at the unit circle here. This is 11 pi over 6, and you can look at a unit circle yourself. And then this is 5 pi over 6. Okay, so we actually have to represent both because there's no way that we can put this together. So if we do the 11 pi over 6, you have to add on that plus 2 pi k, and or theta can equal 5 pi over 6 plus another 2 pi k. And that will cover all of your solutions. So if you wanted to do the quadratic formula just for practice, remember a is equal to 2, b is equal to negative 3. I'm going back to this quadratic here. And c is equal to negative 2 as well. And you can just, I'll set it up for you. You can solve it and you'll get negative 1/2 and 2 for your solutions, but it's x equals minus b, which is negative 3, plus or minus square root, b squared, which is negative 3 squared, minus 4, 2, negative 2, all over 2a. Hey, but wait, a is 2. So change that. So if you simplify this, you will get x equals negative 1/2 and 2. Remember, 2 is not possible. So the last example I want to show you is number 8. Sometimes it's nice to convert everything in terms of sine and cosine, so this might bring you back to identities. Remember, tan theta is equal to sine theta over cosine theta. Cotangent is cosine over sine theta, and that's equal to 2. We're not starting with one side, we're just solving an equation, so it's different than proving an identity. You want to clear the denominators, and in order to do that, you multiply by what's known as the LCD. This is just a great algebra technique, and you'll use this in calculus and in the future. So what is the LCD of sine theta and cosine theta? Well, it's sine theta cosine theta, both of them, because I want the denominators to get absorbed into the top. But if I multiply an equation by something, I have to multiply every term by the same thing to keep it balanced. So now the cosine thetas cancel out, and how many sine thetas do I have? Yes, sine squared theta. Cancel out that sine theta, and it gives me cosine squared theta equals 2 sine theta cosine theta. Now this should, I love this. I love solving these equations because it kind of brings it all together. Because now, what do you recognize about sine squared theta plus cosine squared theta? What does that equal to? Is it the Pythagorean identity? And does it equal 1? Yes, if you thought that, you were correct. Pythag identity. So that's 1 equals, what's this? Double angle. What does it mean? Remember the double angle. So with the double angle, we can say that that is equal to sine of 2 theta. And you can look that up to verify that. That is on page, and I'm looking it up, page 78. So if you wanted to check that out in your text, page 78. Okay, so now this is a lot simpler in a couple of steps. I have sine 2 theta is equal to 1. Well, you're asking yourself, when is sine of whatever equal to 1? What does that whatever have to be? Well, think about the unit circle. Sine, the y value, when you get positive 1, is only up here at the top. This is pi over 2. You could say it's 90 degrees too if you were thinking about degrees, right? But we don't want pi over 2. We want specifically, remember that inside here it's actually 2 theta. So when this stuff is equal to pi over 2, and that would be every plus 2 pi k radians, right? So I would say, when does 2 theta equal that? Does that make sense? It's kind of a strange thing, but you want when the stuff on the inside is equal to pi over 2 plus 2 pi k, because it's not going to give you pi over 2. Think about it. If you plug in pi over 2 right here, you're going to get sine of 2 times pi over 2. Those cancel out. So what's the sine of pi? Well, the sine of pi is actually 0. So that's not what you want. You want that specific thing. And so if we solve for this, theta equals, divide everything by 1/2, or multiply by 1/2. So that's pi over 4 plus, and then the 2's cancel out. So maybe I should just show that to you guys. So what I'm doing here is the 1/2, so they cancel. The 1/2 here and the 1/2 here. So that cancels with that. So it's pi over 4 plus pi over k, or pi k. The 2's cancel. Okay, and if you did, just for fun, for theta, if theta was equal to, or 2 theta was equal to 90 degrees plus 360 degrees times k. So if we were in degree, then you divide everything by 2 here, and you get that theta is equal to 45 degrees plus 180 degrees times k. So what this does, and what this tells me, is that I am dealing with, if I have a pi over 4, and if I plug it in, for instance, think about what sine of 2 times pi over 4 gives you. Cancel those out. That gives you what you wanted. That gives you the sine of pi over 2. So that's why it works. And we know the sine of pi over 2 is equal to 1. Okay, that's the end of this lesson for today. Have a wonderful weekend, and let me know if you have questions.